So, welcome back, students. I am again your sir, Dr. Orko Chaudhary. So, today we'll do another topic in quantum mechanics. It's a very long chapter, as you are seeing. That is applications of Schrodinger equation. Applications of Schrodinger's equation. Okay, applications of Schrodinger equation. So, what is the application? Particle in an infinitely deep potential well. Okay, particle in an infinitely deep potential well, or you can also tell it as a particle in a one-dimensional box. Okay, infinitely deep one-dimensional potential well, particle in an infinitely deep one-dimensional 1D potential well, 1D potential well, or particle in a one-dimensional potential box. Okay. So how will you really imagine this thing? Okay, so let us draw. Okay, so suppose let us first draw the classical picture of the particle. Okay, classical picture of the particle. So suppose there is nothing to draw. Suppose this is a one-dimensional potential well. Okay, this is a rigid boundary. This is a rigid boundary, that is wall. Suppose you take your classroom, for example. Okay, these are the walls of one-dimensional. Your classroom is three-dimensional. You take a one-dimensional classroom, and this is an elastic block. This is an elastic block which is kept inside. Okay, now this is of certain mass, so its mass is very small. Okay, and this wall is so heavy. Suppose you take in your classroom, you take a small rat inside the classroom, chuha. Okay, these are the two walls. So what will happen? It cannot break the wall, and suppose you are also there in the classroom. You are alone, closed in the classroom. You cannot break this wall and go out here. You cannot break this wall and go out here. Okay, this is a frictionless block. Okay, this floor is frictionless. This floor is frictionless. Frictionless floor. This floor is frictionless. Okay, so what is happening here? That this body, this elastic block is coming here. Since this is a rigid wall, it is getting reflected back. Again, it is coming back. Again, it is reflected back. Again, it is so. Since it is frictionless, so neither is any energy lost here, nor is any energy lost here. Okay, suppose you take the example of a rat in the classroom. So it cannot move out of this wall. Okay, it doesn't have that energy to move out of this wall. Okay, so this is the thing. Okay, now let us see the quantum mechanical picture. How the quantum mechanical uh, picture will look like. Okay, so let us consider a particle of mass m capable of moving along capable of moving along the x-axis only between the limits x is equal to 0 and x is equal to L. Okay, the hard walls act as infinitely the hard walls act as infinitely high potential barriers so that the particle cannot escape the box of length L. Okay, so that the particle cannot escape the box of length L. So how will it look like? Okay, so this is the box of length L. This is x is equal to 0 and this is x is equal to L. Okay, and these are the walls. Means outside here, what do you tell, the rigid wall, and here I am telling that it is means outside the potential is infinity. Okay, outside of this wall the potential is infinity. Okay, this is the x direction. Okay, this is the x direction. Outside the wall the potential is infinity. Okay, now the interesting thing here is that since the potential outside is infinity. Okay, the potential outside is infinity, means the particle cannot simply cannot move out of this region. Okay, so what happens here? The potential inside this region is constant. Okay, it doesn't change. No, the potential doesn't change because what? I mean, how is the force rated? F is equal to minus dv by dx. Okay, F is equal to minus dv by dx, and total energy E is what? Kinetic energy plus potential energy. Okay, so I mean, when the kinetic energy will increase, how will the kinetic energy increase? Means suppose like for example, I have drawn many times while discussing in helium neon laser, that is laser produced for helium neon, that is this is a that helium and neon are in the ratio of 5:1. This is a discharge tube. Okay, a potential difference is applied. Because of the potential difference, the electron gain the energy and their energy is increased. Okay, so when that is kinetic energy will increase, when the kinetic energy will increase, they will gain the energy from the potential energy. But here there is no question of gaining any potential energy. There is no question of gaining any potential energy, because here the potential energy outside is infinity, so the potential energy here is constant. Okay, so that is why the potential, since it is constant, that is why it can be chosen as 0. For simplicity of calculation, it can be chosen as 0. So the potential energy the potential energy inside the box the potential energy inside the box is assumed to be 0. Okay, and infinity outside. Okay, so how can you write this mathematically? How can you write this thing mathematically? So inside it is 0. So let me draw this again. X is equal to 0, x is equal to L, here v is equal to infinity, v is equal to infinity outside, and here v is equal to 0. So what will be, how will you write it mathematically? V is equal to 0 for when, and v is equal to infinity for x is greater than equal to L and x is less than equal to 0. Okay, see, the moment x is equal to L and x is equal to 0, the potential becomes infinity. That only have v is equal to infinity for x is greater than or equal to L. At this point, this region, potential is infinity, and this region, when it is less than 0, then also potential is infinity. Okay, but within this region, that is in between x is equal to 0 and x is equal to L, that is in this region, not x is equal to 0 and x is equal to L, x is greater than 0 and less than L. In this region, the potential is 0. Okay, I am again telling you that the concept of the concept of this thing. So here, I mean, the why we are taking potential is equal to 0, because simple thing, that is potential energy, when the potential energy comes, actually when some force is there. Okay, so here basically there is no force at all. Suppose you are you take the example of a rat inside your classroom. Okay, so it can never ever cross this boundary walls. Okay, so definitely, so in that case, you can tell that it has got, when it is not gaining any energy. When will it gain energy? When it will cross this wall or this wall, then only it will gain energy. So there is no question of potential energy coming here. So that is why the potential energy is taken as 0. Okay. Okay, so now so as I said earlier that in the quantum mechanics problem, the main thing, that is the Aadhaar card is the wave function. So you have to find out the wave function. If you know the wave function, from the wave function you can calculate all the other things, that is the probability, the momentum, the energy, everything you can calculate from that. But for that you need to find out the wave function. Okay, so so we have to find psi, and to find psi, what we have to do, we have to, what do we have to do? Tell. We have to solve the time independent Schrodinger equation. You have to solve the time independent Schrodinger equation. To find psi, we have to solve the time independent Schrodinger equation using the boundary conditions. Using the boundary conditions. These are called as the boundary conditions. These are the boundary conditions. Okay. Okay. Now uh, let us do it. Okay. Okay. So where will we solve the boundary condition? The particle is in this region only. So definitely in this region we'll solve the Schrodinger equation. We'll not solve it here at x is greater than L or x is less than 0, because particle is not present here only at all. Okay, so here there will be no Schrodinger equation. Where the particle is present, there we have to find out the Schrodinger equation. So so what will be the Schrodinger equation? d2 psi by dx2 plus 2m by h cut square into e minus v into psi is equal to 0. Okay, but since the particle is in the region, x is less than L is greater than 0. Okay, but since the particle is in this region and v is equal to 0 here, so we can write what we can write: d2 psi by dx2 plus 2m by h cut square into e is equal to 0, into psi is equal to 0. V is 0. Okay, so e into psi is equal to 0. Okay, so this is, say, let us denote it as equation number 1. Okay, let us denote it as equation number 1. Achha, now you see here that this thing, okay, here m is constant, mass is constant, okay, h cut so definitely constant, e is the total energy, okay, E is equal to kinetic energy plus potential energy. This is also is equal to constant. Why it is constant? Now here potential energy is already 0, and so kinetic energy, so it has got a constant kinetic energy. As I said, that it is neither gaining kinetic energy. When will it gain kinetic energy? Only when it will move out of this region, then only it will gain kinetic energy, but it's not moving out of this region. So kinetic energy is constant, so that is why this is constant. So later, so the entire thing, this thing will be a constant then. Okay, so let us take, so let 2me by h cut square is equal to k square. Okay, 2me by h cut square is equal to k square. Okay, now you see the very interesting thing is that why are we taking this as k square? Okay, why are we taking this as k square? The reason behind it is that I had done that wave vector k. Okay, I've done earlier in wave vector k is equal to what? 2 pi by lambda. Okay, now lambda, how you can write lambda? Lambda is equal to h by p by the what law? De Broglie's hypothesis. Okay, by De Broglie's hypothesis, lambda is equal to h by p. Acha. Then 2 pi by lambda. Acha. Sorry, this is 2 pi by h now. 2 pi by. Acha. Another important thing is, acha, e is constant. Now m we have taken constant. Why we have taken m constant? Because I had told that this Schrodinger equation is valid only for non-relativistic particle. That is when the velocity of the particle is much less than that of the velocity of light. I had discussed it earlier here. Okay, Schrodinger equation is valid only for non-relativistic particle. Okay, you see here Schrodinger equation is for non-relativistic particle. Okay, Schrodinger equation is for non-relativistic particle. That is why the mass is constant. We can take the mass as constant. But if it is nearing the velocity of light, then the mass will vary. Okay, so this is 2 pi by h. Acha, p will be what? P you can write is square root of 2me. Okay, you can write p as square root of 2me. Okay, acha, so you can write this as square root of 2me by h by 2 pi, that is h cut. So so from here you see that here k is equal to square root of 2me by h cut. So this is square root of 2me by. So this and this are the same thing actually. This k and this k both are basically the wave vector. Both are basically the wave vector. This k and this k both are basically the wave vector. Okay. Okay. So now how will this equation turn out to be? d2 psi by dx2 plus k square psi will be equal to 0. Okay, d2 psi by dx2 plus k square psi will be equal to 0. Okay, so what will be the solution? The solution of this. What will be the solution? Solution of this equation will be. Solution of this equation will be psi will be equal to a sin kx plus b cos kx. Okay, a sin kx plus b cos kx. This will be the solution. Okay, so now we have where a and b are the are arbitrary constants. Means how have we found out this constant? We have found out basically by solving this by integration. You have found out. Okay, Achha, now you have to apply the boundary conditions here. Okay, so at there will be two conditions at x is equal to 0 and x is equal to L. So at x is equal to 0, okay, at x is equal to 0, what happens? At x is equal to 0, psi becomes equal to a sin 0 is 0, so 0 plus b into cos 0, cos 0 is 1, so therefore psi is equal to 0 plus b. Achha, but at x is equal to 0, what happens? V becomes infinite. But at x is equal to 0, V becomes infinite. So I mean, at x is equal to 0, V becomes infinite. That is, at x is equal to 0, the particle cannot come here at x is equal to 0. Okay. At x is equal to a, x is equal to L, V is equal to infinity. Okay, at x is equal to 0, V is equal to infinity, and x is equal to L also, V is infinity. Okay, so you see here, so at the walls, what happens? At x is equal to 0 here, V is infinity. At x is equal to L also, V is infinity. So here the wave function will vanish, because at this region, what is wave function? Wave function, first of all, what are the properties of wave function? See, here I have done the properties of wave function. Must be continuous, single valued at each point in space and finite. It's a very important property. Psi must be continuous. Now at till from x is equal to 0, here in this region psi is continuous. Psi will be continuous because the particle is present here. Here the particle is not present only. Okay, after the point at which x becomes L and x becomes 0, the particle stops to be present. Here particle is not present. So and after this the wave function will be discontinuous. There will be a discontinuity because here, okay, there is a constant potential. There is a constant potential here. Suddenly the potential becomes infinity. So definitely there will be a discontinuity. Okay, suddenly the potential is infinity here at x is equal to 0. Suddenly the potential is infinity at x is equal to L. So definitely there will be a discontinuity here. So psi will be, the wave function will be 0 at x is equal to 0 and x is equal to L. Okay, so therefore psi is equal to 0 at x is equal to 0 and psi will be is equal to 0 at x is equal to L. Okay, psi will be 0 at x is equal to 0 and psi will be 0 at x is equal to L. This is the thing, because first of all from the condition that psi must be continuous to be well behaved. Psi must be continuous. Now at x is equal to L, suddenly the potential becomes infinity. So here it will lose its continuity. At x is equal to 0, suddenly the potential becomes infinity. So it will lose its continuity. Okay. So let us apply the this boundary condition here. Let us apply the boundary condition. So at x is equal to 0, so at x is equal to 0, what are you getting? You are getting here on the right hand side, you are getting b, because sine 0 to 0, so the a into 0 is 0, so b. And at x is equal to 0, therefore from here b will be equal to 0. From here we can write, since at x is equal to 0, psi is 0, so from here we definitely write b is equal to 0. Okay, so what is remained here? Therefore what comes? Psi is equal to a sine kx. Okay. The wave function comes now as so psi is equal to a sine kx. Okay, now let us apply the second boundary condition. Where we have here we have applied this condition. At x is equal to 0 we have applied here. Okay, at x is equal to 0 we have applied. Now we will apply here at x is equal to L. We have applied here at x is equal to 0 we have applied. At x is equal to 0, psi is equal to this a sine 0 means 0 plus b cos 0 and b. Then we have applied this. Okay, now we will apply it at x is equal to L. Okay, at x is equal to L. Okay, again at x is equal to L. See here at x is equal to L, v is equal to infinity, at x is equal to L, psi is equal to 0. So we will write psi is equal to 0. And we have already found out b is equal to 0. So only this is left, a sine kl is equal to 0. Okay, so here either a is equal to 0 or sine kl is equal to 0. Okay, either a is equal to 0 or sine kl is equal to 0. Now what will happen, that we have to see what is right. Is a 0 or sine kl 0? what is 0 here? Acha, now you see here that ultimately the wave function come out as a sin kx. Okay, acha, now you see here, let me do it here only. See here, say suppose what is probability? Probability is mod of psi square, right? So psi square will be what here? Means here it is a sin k l. Okay, so means psi square will be what? Will be proportional to a square, right? Now if a is equal to 0, what does this prove? If a is equal to 0, proves that psi is equal to 0. But if psi is equal to 0, now what does this mean? If psi is equal to 0 means we are seeing inside the well. If psi is equal to 0, that means what? The particle is not present here only. So this cannot be possible. Okay. If psi is equal to 0, this means that particle is not present inside the well, which is completely wrong, because particle is definitely present inside the well, which is completely wrong. Okay, suppose let me draw the particle here. Suppose like here I've drawn the particle. Okay, so let me draw the particle. So suppose it's say here, this is the particle. Okay, suppose it is say here, this is the particle. Okay, so which is completely wrong. That means that the particle is not present inside the well, which is completely wrong. So therefore a cannot be 0. Therefore a cannot be 0. Okay, therefore what will you do? Therefore let me do here. Therefore sin kl must be equal to 0. See here, either a is equal to 0 or sin kl is equal to 0. Now a is not equal to 0, we have proved. Therefore sin kl must be equal to 0. Now sin kl 0 means what? Kl will be equal to n pi, where n is equal to 0 plus minus 1 plus minus 2, like this. Now here also there is the physics here. So therefore what will you get? K is equal to n pi by L. Okay, K will be equal to n pi by L. Achha, now say for n is equal to 0. So for n is equal to 0, K will be equal to 0. Right? Now K will be equal to 0 means what? K is what we have found out. K is what? 2 pi by lambda. Okay, K is 2 pi by lambda we had found out. Here we had found out. You see here, K is 2 pi by lambda. From here only we have done square root of 2 by e square. Okay, now 2 pi by lambda and K is 0 means what? Lambda is infinity. Now this is not possible. Lambda cannot be infinity. Therefore K cannot be equal to 0. Okay, therefore K cannot be equal to 0. Therefore we cannot take therefore n is not equal to 0. Okay, therefore n will not be equal to 0. Therefore what will be the condition? What will be the condition here? Therefore K is equal to n pi by L. K is equal to n pi by L. N must be equal to plus minus 1, plus minus 2, plus minus 3, etc. like this. Okay. This will be the actually the solution. Okay, so what will you get here? Therefore, the psi will be equal to a sine n pi by L into x. This will be the solution. Psi will be equal to a sine n pi by L will be the solution. Okay, now you see again at the normalization. Now this is a normalized wave function, but this normalization constant, this is the normalization constant, which is unknown. So you have to find it. How will you find it? By applying the normalization condition. What is the normalization condition? What is the normalization condition here? Uh, this is the normalization condition. That is, you have to integrate psi star psi. Okay, you have to integrate psi star psi. See here, I have written any unnormalized wave function can be normalized by finding the norm. In psi star psi, beta is equal to n. You see here, this psi is this, psi star is this. We have done psi star psi. From here, we have calculated a. Okay, a is 1 by root 2. So similarly here also we will do that. So integration of psi star psi into d tau is for 3 dimension, but this is not 3 dimension, this is 1 dimension. So this is psi star psi dx, and here it was, I think, see, -1 to +1. I mean, here what will be the integration limit? Integration limit means where is psi valid, basically. Psi is valid between x is equal to 0 and x is equal to L, because here only the particle will be present. So where the particle will be present, there only psi will be also valid. Okay, so this will be integration of 0 to L psi star psi dx will be equal to 1. Okay, so integration of 0 to L, here complex conjugate of this is this only. So mod of a square into sine square n pi by L into x dx will be equal to 1. Okay, so here mod of a square by 2 integration of 0 to L 2 sine square x dx. So means 2 sine square theta d theta formula. So 1 minus 2 sine square theta. So 1 minus cos 2 n pi x by L into dx will be equal to 1. So or here, or mod of a square by 2 into integration of I am not writing the integration, I am directly writing this will be x, and this will be L by 2 n pi into sine 2 n pi x by L into 0 to L is equal to 1. Okay, this will come out to be 0. Everybody, if you don't understand, you do it yourself, you will get. So this will be L minus 0, so that is L only. This will be equal to 1. So therefore A will be what? A will be square root of 2 by L. A will be square root of 2 by L. So from here you can write what? From here you can write psi will be equal to square root of 2 by L into sine n pi x by L. Okay, this will be the normalized wave function. So now these are basically the normalized wave function. This is the normalized This is a normalized wave function or the eigenfunction. Normalized wave function or the eigenfunction. Okay, now you have to find out the energy eigenvalue. Energy eigenvalue or simply the energy value. So how will you find it out? You will find it out from this equation. 2me by h cut square is equal to k square. From here what will you get? E is equal to k square h cut square by 2m. So E will be equal to h cut square k square by 2m. Okay, so h cut square by 2m into k square. What is k here? Simply write the value of k. K is what here? K is n pi by l. So k square by n square pi square by l square. So n square pi square by l square. So E you can write, since it depends on n, so E of n will be equal to n square pi square h cut square by 2m l square. Okay, by 2m l square. So here what do you get? E1 will be what? E1 is called as the ground state energy, on a lowest energy, ground state energy. E1 will be the ground state energy. E1 will be what? Pi square h cut square h cut square by 2ml square. Okay, so E1 is the ground state energy. Now you see ground state energy means lowest energy. So lowest energy, this is not zero. Okay, for classical particle, the ground state energy will be zero. This is the difference between classical mechanics and quantum mechanics. For classical particle, E1 will be equal to 0. Okay, for classical particle, E1 must be equal to 0. But for quantum particle, no, it is not 0. Okay, this is also called as 0 point energy. This is also called as a 0 point energy. That means, and at ground state also there is some energy present in the particle. There is some the energy present in the particle. Now what is the reason? What is the reason behind this? The reason behind this is the Heisenberg uncertainty principle. Heisenberg uncertainty principle. Okay. Now what is the Heisenberg uncertainty principle? Delta x into delta p is greater than equal to h cut by 2. Okay, delta x into delta p is greater than h cut by 2. Now delta x is what here? Delta x, uncertainty in the position. What can be the uncertainty in the position? This can be one. It can be anywhere. It can be anywhere between x equal to 0 and x equal to L. So uncertainty in position is definitely this L. Okay, so here delta x is equal to L. Delta x is equal to L. So delta p will be what? Delta p must be greater than or equal to h cut by 2L. So definitely it is not 0. It is finite. So definitely it is finite. Delta p is finite means what? Delta p is finite means what? The energy, that is kinetic energy, is what? P square by 2m. It doesn't have potential energy, so P square by 2m. So that is finite. So this means therefore the kinetic energy is finite. It cannot, kinetic energy is not 0. That is why the total ground state energy is also not 0. Okay, that is why the total ground state energy is also not 0. And that is why from here, that is means for liquid helium helium. Okay, liquid helium is what means I mean you are liquefying a gas. You are liquefying a gas. Okay, when you want to liquefy a gas, how do you do it? You gradually you decrease its thermal energy. Okay, now at 0.0001001 Kelvin also, at this temperature also, it is not sorry liquid helium, and you want to solidify it. So at this low temperature also solidify. How do you solidify it? Like water, how do you solidify? You decrease the temperature of water. At 0 degrees Celsius it liquefies. Okay, but liquid helium at 0.001 Kelvin also it does not solidify. So this is also another example of this Heisenberg uncertainty principle. So now how will the wave function, this is the wave function, so how will the wave function and the probability, how will it look like? Okay, now before telling this, I want to tell you that what happens here is that I mean this is the particle. What happens? The particle moves here. This is an impenetrable wall, that is almost reflecting wall. So it comes here and hits the wall, and it again comes back like this. Again hits the wall like this, and again it comes back. So that the same thing as like that laser happens. It's kind of mirror. So gradual reflection and coming back, reflection and coming back. This thing happens, and as a result of this, what happens? A standing wave is produced here. Okay, as a result of this, a standing wave is produced here, and it behaves as a free particle. It behaves as a free particle. Okay, why does it behave as a free particle here? Inside the box, why does it behave as a free particle? The reason behind this is that let me write it. So inside the box, no force. Okay, no force. Free particle means what? Basically free particle is which is free, means there is no force acting on it, no potential energy. Potential energy, what it binds it. Okay, free electron. What is a free electron? Free electron means its binding energy is 0. That is potential energy is 0. Okay, so inside the box no forces act upon the particle. Inside the box no forces act on the particle. Inside the box no forces act on the particle, which means that the part of the wave function, which means that the part of the wave function inside the box, the part of the wave function inside the box oscillates through space and time, oscillates through space and time with the same form as a free particle, Okay, you see it oscillates. It hits here, again comes back, hits here, again comes back, hits here, again comes back. This oscillation gradually takes place, and as a result of this oscillation, you have seen, just like in laser, this the standing waves are created. Okay, so actually this solution which I have done here, this is the solution. This solution is basically a free uh, a free particle solution. Okay, this solution is basically a free particle solution. Okay, so from here only you can see. So if you draw the well here like this, this is the level n is equal to 1. Okay, okay, so for that what will you get? This psi 1 will be what? Square root of 2 by L into sine pi x by L. Okay, so what will be this? See, at x is equal to 0, at x is equal to 0, sine 0, so it's 0. At x is equal to L, sine pi, so 0. Okay, and x is equal to, say, this is L by 2, so what will you get? Sine pi by 2, so it will be maximum. So how will it look like? Exactly like this. Okay, this is psi 1. Acha, then psi 2, that is square root of 2 by L sine of n pi x by L, so 2 pi x by L. Okay, so you see here again, at x is equal to 0, 0. At x is equal to L, it is sine 2 pi, so 0. At x is equal to L by 2. See, interesting. At x is equal to L by 2 also, this is L by 2 you do, so sine pi, so 0. So how will it look like? At x is equal to, say, at x is equal to, this is n is equal to 2. Okay, n is equal to 2. How will it look like? It will look like this. This. Okay, then like this, say this is n is equal to 3. This is n is equal to 3. At x n is equal to 3, psi 3. This will be square root of 2 by L sine 3 pi x by L. Again here also you see, at x is equal to 0, sine 0, 0. So at x is equal to L, this is x is equal to 0 and this is x is equal to L. At x is equal to sine 3 pi 0. At x is equal to L by 2, so 3 pi by 2. 3 pi by 2 will be what? 3 pi by 2 will be pi minus pi by 2. So again it will be it will be maximum. Okay, and it will be all sine. So this will be sine of 3 at x is equal to L by 2. This will be 3 pi by 2. So sine of pi plus pi by 2. 2 pi plus 3 pi by 2. So this will be minus 1. So it will be a maximum in the negative direction. So how will it look like? It will look like this. Like this. I've not drawn exactly. Try to draw it symmetrically. Okay, this will be this will be psi 1, this will be psi 2, this will be psi 3. Achha, now how will the year look like? So let me draw it here. Psi square. How will psi square look like? And this is x is equal to 0, this is x is equal to L. Okay, how will psi square look like? Psi square will be, psi can be negative, but psi square will always be positive. Okay, psi square will always be positive. So psi square will be like this, similar to this, but its magnitude will be larger. This thing will be exactly at the middle. Okay, I've not drawn it at the middle. Acha, then you will get, this is psi 1 square. Acha, now this will be psi 2 square. How will psi 2 square look like? Psi 2 square, there will be two like these peaks. Okay. Acha, psi 2 square, there will be two peaks. Acha, but at the middle here there will be this thing will be 0, like this. Okay, so like this. Then for psi 3 square there will be 3 peaks like that. Okay, so this is the thing. Okay, so this thing will look like this. The wave function will look like this. Another thing is that I had done E1 ground state energy, that is this is this thing. Achha, let us do now E2. Okay, let me do it here only. E2 will be what? E2 will be this will be n square pi square. So 2 square pi square h cut square by 2 ml square. So what will be that? 2 square into pi square h cut square ml square will be E1. 2 square into E1. Acha. E3 will be 3 square into pi square h cut square by 2 ml square. So this will be 3 square into E1. Okay. So what are you seeing here? You are seeing that I mean, again here these are discrete values. Okay, this is E1. Then next one is what? Next one is 4E1. Next one is 9E1. Okay, then there will be E4 will be what? E4 will be 4 square E1. Okay, so 16E1. So gradually you see the gap increases. So 4 to 3E1, then 4 to 5E1, then here is 7E1. So gradually the gap increases. Okay, and another thing is that again you see here these are discrete, not continuous. First is E1, then is 4E1, means. So here it clearly proves that this is discrete. Now if you for example you take money, it is kind of a ladder. If you are like this is a ladder. So this is the first step of the ladder. Okay, then this is E1. Okay, then this is say 1 2, I mean, so this is 4E1, the second one. After 4E1 this again increases more. So this is 5E1. Okay, after that this is 9E1. This is 9E1. Then after that again it increases more. The difference increases more. Say 16E1, like this. This is 16E1. Okay, so in this case it's like a ladder. You can imagine the suppose if I tell you that okay, your position is at 3.5E1, no, it will not happen. It's discrete. Okay, but if you take say a rope like this, and in a rope, what you can tell? This is discrete. In a rope, if I tell okay, you take your position 3.5E1, then you can tell okay, yes, you can take. Okay, so this is the difference between quantum and classical. Okay, and another thing I wanted to tell is that here this constant E1, this E, okay, 2m E by h cut square. See here, this is square root. Okay, now we have assumed here, we have assumed E to be positive. We have assumed E to be positive. Okay, why we have assumed E to be positive? Okay, why? So suppose E is negative. Okay, suppose E is negative. Okay, so suppose E is negative here. See here, E is negative. Then what will happen? K will be what? K will be imaginary. So then K will be imaginary. Okay, K will be imaginary. So so then if K is imaginary, then lambda will be imaginary. Lambda will be imaginary. Okay, that is not possible. That is not possible. Okay, therefore E has to be positive values. E cannot be negative values. Achha, and another thing is that here this K value, where have I taken K? This K here, I have taken, the question might arise to you, okay sir, you have taken plus minus, both values you have taken. Why you have not taken 0, I have told you. Now K I have taken plus minus value also I have taken. Okay, now you see here, if I take but generally I have taken, means I have done all the calculations taking n as 1 only. Okay, now if I take n as, say, if n is negative, n is equal to -1. Okay, then what will be the solution? Psi will be what? Psi will be psi will be a into sine of minus n is 1 minus n pi x by L. So this will be what? Minus a sine pi x by L. Okay, so now you see the, what did I tell? This constant is an arbitrary constant. Okay, so if you take minus a as another constant, say as c sine pi x by L, that is also a constant only. Minus is a constant, so no problem, you can take minus a as c. Okay, so the n can have two values only, plus minus both values only n can have. Okay, and another thing is that just remember that this is E is n square pi square h cut square by 2ml square. So the energy of the any nth state of the particle is directly proportional to n square. Pi and h cut are constant, is inversely proportional to m, and is inversely proportional to the L square, that is dimension of the potential value. Okay, so thank you very much. So study this nicely. So based on these various questions will be asked, when I'll take the test, I'll ask MCQ questions from here. Some problem also I can give from here. Thank you.